Hi class, in this lecture we're going to talk about Chapter 15. We're going to talk about the beginning of Chapter 15, which talks about surveying the stars. That's actually the whole chapter, but we're going to talk about our particular properties of stars, and in particular, luminosities. So what is luminosity? Luminosity is how bright the star is, how much energy every second it's giving off. So how do we figure that out? If we can't go visit the stars, if we can't be near the star, we can be close to our sun, but what about all the other stars that we see? How do we know how bright they truly are? How much energy per second they're giving off? So we'll talk about that. And then in the next lecture, we'll talk about temperatures. And then the one after that, we'll talk about masses. How do we determine how much mass the stars have? So how do we measure stellar luminosities, actual brightnesses, energy per second given off by a star? If we look at this picture, you can see that stars look different. They look like they have different brightnesses. These stars, these kind of brighter ones, this one here is very bright. All these other ones are fairly dim. You can see some really dim ones in there. So clearly stars have different brightnesses, but are they all, truly different in brightness? Do they perhaps all give off the same amount of energy every second? Well, the answer is no, they don't. But how do we figure that out? How do we figure out how much energy every second they actually give off? Clearly these stars look like they have different brightnesses, but it's actually because either they don't have different brightnesses to begin with, or if they do have different brightnesses, then they might be different distances away, and so they don't look like they don't look like they have the same brightness. So we're actually going to use the word brightness to refer to how the star looks to us, and we'll use the word luminosity to describe how bright the star truly is. If you were the same distance away from every single star in the universe, you would be able to make an easy comparison between their true brightnesses or their luminosities. So we have to somehow take distance into account. So again, luminosity is the total amount of energy every second that a star gives off. So energy per second is also written as watts. Think about a light bulb. A light bulb is like a 60-watt light bulb. It gives off 60 joules of energy every second. And that energy gets spread out over an area, and the energy kind of spreads outward in all directions from the light bulb. So the same thing is true about a star. The star produces a certain amount of energy every second, and that energy goes outward in all directions away from that star. The apparent brightness, or just plain old brightness, if you want to think about that, is how the star looks to us, how bright the star appears to be, the apparent brightness. How bright the star appears to be. And that depends on distance. That depends on how much energy every second is hitting your telescope, for example. And the further away you are from that star, the less energy every second is hitting the telescope. The star is going to not look as bright. If we think about two stars, Alpha Centauri and the Sun, they are both actually similar. They're fairly similar. They both have, it turns out, very similar luminosity, very similar actual true brightness. Which one actually appears brighter? Well, which one's further away? Alpha Centauri is further away, definitely much further away than the Sun. The Sun is really close. It's our closest star. And so clearly the Sun is going to appear much brighter because it's much closer. So even though those two stars are almost the same in terms of their true brightness, their luminosity, the Sun definitely looks brighter because it's much closer. So this figure gives a good idea of how this works. If you think about a star in the middle of this figure here, there's a star there that gives off a certain amount of energy every second. And that energy travels outward away from the star in all directions. And if we kind of think about an imaginary ball surrounding the star that has a radius of 1 astronomical unit, that's the distance from the Sun to the Earth, that ball, all that energy that the star is producing every second, is going through that ball. Every second, the same energy that the star produces goes through that ball. And so if we look at a particular direction, if we look at a particular sort of area, this little square here, there's a certain amount of area on that 1 astronomical unit radius ball. There's a certain amount of energy every second that's going through that square. Right? A certain amount of energy every second that square is kind of capturing as the light is coming from the star going through that square. Well, because the light spreads out as it goes, if we consider another ball, imaginary ball, that has a radius of 2 astronomical units, all the energy that goes through that square at the 1 astronomical unit distance ends up going through 4 squares. These are all the same size squares, but now there are 4 of them that energy goes through when I double the distance from 1 astronomical unit to 2 astronomical units. If I triple the distance, if I imagine a ball of radius 3 astronomical units, all that same energy every second that the star produces goes through that ball. But how much goes through just this part, that the energy that goes through this 1 square here at 1 astronomical unit? All that energy just keeps propagating outward. It ends up going through 9 squares. Again, all these squares are the same. All that energy goes through 9 squares once it gets out to the 3 astronomical unit distance. So the amount of energy every second in 1 square at 3 astronomical units is 1/9. There's 9 of these squares here that make up the same energy every second through this 1 square at that closer distance. And so 3 astronomical, I've increased my distance by a factor of 3 from 1 astronomical unit to 3, and the area that energy is going through has increased by a factor of 9. And so that same energy every second that is going through that 1 square is going through 9 squares. So the actual kind of the brightness that you might see if you imagine having a telescope that was one of these squares, the telescope out at 3 astronomical units would be capturing only 1/9 of what the telescope at 1 astronomical unit would be capturing. In other words, the brightness, the apparent brightness, would go down by 1/9, by a factor of 9, 9 times dimmer at 3 astronomical units than at 1 astronomical unit. And so what you do is you take the luminosity, again, which is the energy created by the star every second, you divide that by the area of the sphere at the distance that you're observing. And so again, you're some distance from the star, there's kind of an imaginary ball around the star that has a radius equal to the distance that you're at. You take that luminosity and divide by the area of that sphere, because all the energy that the star is producing is going through the area of that ball. And the area of a ball is 4 pi times the radius squared. And you divide the luminosity by that area, and that's what gives you the brightness. So brightness, how bright the star looks, is the energy every second the star gives off divided by the area of a sphere of your distance that has a radius equal to your distance. And so the area is 4 pi distance squared. And so if you multiply this, if you take this equation and just multiply both sides by 4 pi distance squared, you get this, that the luminosity of the star is 4 pi times the distance squared times the brightness that the star appears to be. So if you can measure how bright the star appears to be, and you can measure your distance to the star, you can calculate how truly bright the star is. What is the total energy it gives off every second? So that's what we're going to do. We're going to talk about, we can easily measure the apparent brightness. You just use some device that measures how bright a star is. And then you somehow figure out distance. So they have to figure out the distance to the star. Once you do that, then you take these two things, multiply them together, and you get the energy every second that the star gives off. That's a true characteristic of the star that doesn't depend on who's observing it. It's a property of the star itself. So again, and you can see that if you go back to this top equation, a particular star has a luminosity that doesn't depend on who's looking at it. It's just how much energy every second it gives off. But if you take your distance and multiply it by 3, like we did in the last page, in the last figure, the 3 gets squared, that becomes a 9. So we have a 9 on the bottom. That means the brightness will go down by a factor of 9 compared to a distance of, let's say, 1 astronomical unit. A distance of 3 astronomical units would have a brightness 1/9 the brightness at 1 astronomical unit. So how would the apparent brightness of Alpha Centauri change if it were 3 times farther away? So right now it's a certain distance, and it looks to be a certain brightness. But what if we made its distance 3 times farther than it actually is? Changing the distance by a factor of 3, you're going to get 3 squared in the bottom. That's going to change the brightness by a factor of 1/9. It's going to reduce the brightness by 9 times dimmer than it was before. So it would be only 1/9 as bright. So this is what's often called the inverse square law. There's a couple different things in physics where there's equations that depend on 1 over the distance squared. And the way light behaves and how brightness behaves, depending on distance, is one of those things. So if you have a source of light that's giving off energy in all directions, that energy spreads out and goes through, these various imaginary spheres. The energy spreads out over the area of a sphere as it travels, and the area of a sphere depends on the distance squared. And so the brightness is dependent also on distance squared, 1 over distance squared. And so if you double your distance, the brightness goes down by a factor of 4. If you triple your distance, the brightness goes down by a factor of 9. If you quadruple your distance, the brightness goes down by a factor of 4 squared, or 16. And so there's this squared, inverse squared relationship. So we need to figure out distance. It's really important. How do we determine how far away these stars are? So we can't really say anything in particular about, comparing directly this star, for example, with this star. This star here looks brighter than this star, but is this star truly brighter, or is it just closer to us than this star? Could this star be really, really bright, a really, really big energetic star? It's possible. We have to know the distance. How do we do that? What we do is use a technique called parallax. And what it is it's the apparent shift in position. So the word apparent again means it appears to shift in position. It isn't really shifting in position. It just appears to be shifting in position. It's the apparent shift in position of a nearby object against a background of more distant objects. So if you think about as you're driving down the road and you see some trees kind of close to the road, but then there's other trees way far away across some farm fields, it looks like the position of the nearer tree is changing relative to the farther trees as you're moving down the road. And that's only because you're observing the tree, the nearer tree, at different angles as you're traveling. And as you're looking at the nearer tree, you see the background trees in slightly different places. It appears as if that closer tree is moving relative to the farther away trees. The trees aren't really moving, it's you that's doing the moving, but it appears as if the closer tree is moving. So in the same way, if we look at a star as the Earth goes around the sun, we see that the closer stars, appear to be moving relative to the farther away stars. But they're not necessarily moving relative to each other. It's really that the Earth is moving, and you're viewing the closer star from a moving Earth, just like you might be viewing a closer tree from a moving car. And so you see the star, like you see the tree, changing position relative to the farther away stars or trees. And you can measure some kind of an angle, an angular shift in position. And that angle is called the parallax angle. And if we can measure that angle, and knowing about how the Earth is moving, we can get, and using some simple geometry, we can get a decent measurement of the distance to some nearby stars. So here's a figure that shows that. If we look at, if we imagine that it's in January and we're looking at this particular star right here, this is a closer star to us, to the Earth. When we look at the star in January, we look in this direction. And we see these other stars. We see this star kind of close to it, this star, this star, this star, and this star. So when we look in this direction, this is the picture we see right here. That star right there is this guy right here. Right? This star is maybe this one right here. This star is this one right here. This star is this one over here. And so in January, we look at this closer star and we see it in this position relative to these other stars that are further away. If we let the Earth go around halfway around its orbit, and in July then we look at that same star, we look at it in a different position relative to the star, the background stars. So notice in these two pictures, these white smaller dots are the farther away stars, and they haven't changed. They're the same. But the nearby star in January was in this position. In July, it's in this position, seen in this photograph. So you take two different photographs 6 months apart, and you see a shift in the position of a closer star. And you can measure an angle. You can measure an angular shift. And so knowing the distance that the Earth is from one position to the other, 2 astronomical units from this position, to this position. That's a 2 astronomical unit, what we call baseline. And measuring the shift in the sky from one point to the other, we can measure this angle, big angle here, the angular shift of the star. Half of that angle is what we call the parallax angle P. So we measure that parallax angle P very carefully with some device or some measuring device. We're looking at these photographs and we're very carefully measuring the angular position from where the star was initially to where it is now. And then we can get half of that then is the parallax angle. So then knowing the distance from the Earth to the Sun, this is 1 astronomical unit. This is some triangle here. This is a triangle, right triangle with a 1 astronomical unit base. We're trying to find this hypotenuse. This is our distance, or this here as well. In reality, this is a really, really skinny triangle. These angles are really, really tiny. Okay. And this distance from the star to the sun is almost the same as this distance from the star to the Earth. We're talking about, comparing 1 astronomical unit of distance to many, many light years. The 1 astronomical unit distance is very small. This is really a very skinny triangle. Okay? So we can do a little bit of geometry and we can find very accurately this distance. And so this is an equation that we can talk about. What we do is we define a particular distance called the parsec. In astronomy, you might have heard of distances to stars in parsecs. And what a parsec is it's a star that has a parallax angle of 1 arc second. And so if you remember back to angles, we can break a circle up into 360 degrees. We can break a degree up into 60 arc minutes. And then we can break an arc minute up into 60 arc seconds. So an arc second is a very small angle. And if a star shows a shift in position among distant stars of 1 arc second, it's a very small distance change. It's a very small angular change. But if we can measure that, then we know that that star is 1 parsec away. That's the definition of the distance, 1 parsec. It has an arc second or a parallax par of 1 arc second. Parallax second, parsec. The parsec is the star that has a distance, or has a parallax angle of 1 arc second. We can convert that distance into light years. 1 parsec is also 3.26 light years. So if we want to calculate the distance in light years, we take 3.26 and multiply it by 1 over this angle in arc seconds, right? So the distance in parsecs is just 1 over the angle in arc seconds. The distance in light years is 3.26 times 1 over the angle in arc seconds. So if there was a star that had an angle of 2 arc seconds, it had a parallax angle of 2 arc seconds, then you would have 1 over 2 parsecs. That would be 1/2 of a parsec. That would be the distance. If you had a parallax angle of 1/2 an arc second, then this would be 1 over 1/2. 1 over 1/2 is 2. That would be a distance of 2 parsecs. And so we can accurately measure the distances of nearby stars if we can see their shift in position among other stars as the Earth goes around the Sun. This is limited, though, to the nearer stars. We can't use this with stars that are really far away because those angles get really, really tiny and they become really hard to measure. So we'll talk about other techniques of measuring distance. We can only use this for stars kind of near us within our own galaxy. We can't use this for stars beyond our galaxy. That's definitely certain. And we can't even use this for the majority of stars in our own galaxy. This is only for stars kind of in our neighborhood, several light years away. But telescope technology is getting better and better, so these distances are measuring distance by parallax is getting easier and easier. So in terms of luminosities then, once we've determined distances to these stars, we can then measure their brightnesses, their apparent brightnesses, figure out their distances, and calculate their luminosities. And what we find is that some of the brightest stars, the truly brightest stars, the most luminous stars, can be 1,000,000 times as luminous as the Sun, 10 to the 6. So you could have a star that's giving off 1,000,000 times as much energy as the Sun does every second. That's a pretty incredible star. And you could have stars that are very dim, that have a very low luminosity, 10 to the minus 4 or 1/10,000th as luminous as the Sun. So fairly dim stars as well, and there's a lot of those. There's actually a lot more very dim stars than there are very bright stars. And as we'll talk about, as we'll see, these very, very bright stars don't live as long as the very dim stars. And so you see a lot more very dim stars out there because they live longer. They don't die as quickly. So this slide shows something called the magnitude scale, and we've talked about this a little bit before. The magnitude scale is a little bit funny because it's kind of a backward scale. So we use little m to represent what we call the apparent magnitude, how bright the star appears to be. And the numbers, again, are backwards. And so let me just give an example. Suppose I have one star, we'll call it star number 1, that has an apparent magnitude of 5, the number 5. And then we have another star, M2, or star 2, that has an apparent magnitude of 0. It turns out that the star with a 0 magnitude is actually a brighter looking star than the star with a magnitude of 5. So it's kind of a backward scale. And then there's something called absolute magnitude, which has more to do with how truly bright the star is. If you had two stars that were the same distance away, you could compare directly how truly bright they are. So the absolute magnitude is more of a comparison of the luminosities, and the apparent magnitude is more of a comparison of the apparent brightnesses. And so we'll look at those. So these two equations allow you to calculate not the actual brightness of one of the stars, but just how two stars compare with each other. So the apparent brightness of star number 1 divided by the apparent brightness of star number 2 is given by this stuff over here on the right. You take 100 and raise it to the 1/5 power. But don't actually do that. Don't actually calculate that yet. But then you take that and then you raise it to this power, m2 minus m1. So you subtract the two magnitudes, 2 minus 1. And then that is the power that you raise this 100 to the 1/5 power 2. So in this example, when I look at that, so I've got 100 to the 1/5 power, so 1 over 5, kind of a small 5. So 100 to the 1/5 power. And then I'm going to raise it to the m2 minus m1 power, so 0, so 0 minus 5. All right. So I've got 100 to the 1/5 to the 0 minus 5. So 0 minus 5 is minus 5. So this is going to be 100 to the 1/5 power, whatever that number is. Don't worry about it just yet. We'll calculate it in a second. But I'm going to raise that to the minus 5th power. So when you do powers, when you do some number raised to a power and then raised to another power, you just multiply these powers together. So 1/5 times minus 5. So that's going to be 100 to the 1/5 times minus 5. Well, 1/5 times minus 5 is minus 1. So that's 100 to the minus 1. 100 to the minus 1 is the same as 1 divided by 100. So 1 divided by 100. And so what that is, that's the stuff over here on the right. So that's the ratio of the apparent brightness of star 1 to the apparent brightness of star 2. So I can write this as, I'm going to call it apparent brightness, so AB1 divided by AB2, apparent brightness of star 2. And so if I take this equation and then maybe just multiply both sides by AB2, I get that 1 over 100 times AB2 is equal to AB1. And so what this says is that the apparent brightness of star number 1 is 1/100th the apparent brightness of star number 2. Star number 1 appears 100 times dimmer than star number 2. And so a difference in magnitude of 5, 0 to 5, or any difference in magnitude of 5, any two magnitudes where the difference is 5, the apparent brightnesses are different than by a factor of 100. One star is 100 times brighter than the other, apparent brightness in this case. So that's how you use these equations. In the first one, again, it's just comparing the apparent brightnesses of the two stars. And so for that, you look at the difference in the two apparent magnitudes. And the second equation is exactly the same thing. You're comparing the actual energy produced by the star every second, the luminosity of the two stars. And so it's exactly the same equation, but you subtract the absolute magnitudes. And to find these absolute magnitudes, you have to know the distances to the stars. To find apparent magnitudes, you don't need to know distances. You just look out at the sky and you just measure how bright each star appears to be. And you kind of rank them according to this magnitude scale. And so again, the magnitude scale is kind of backwards. Bigger numbers mean dimmer stars, and that's true for absolute magnitude as well. Bigger absolute magnitudes mean dimmer luminosities, lower luminosities. And so there's a direct relationship between absolute magnitude and luminosity. But to get from apparent magnitude or apparent brightness to luminosity, you need to know distance. So we talked about how you figure out distance. So in the next lecture, we'll talk about temperatures. How do you determine the temperatures of stars? And then eventually we'll figure out how do you determine the masses of stars. And ultimately we'll start to see some patterns between temperature, brightness, mass, and lifetime. So there's all kinds of interesting patterns that we'll eventually discover.